Welcome back to this next video in the playlist on Galois theory. In this video, we're going to talk about the topic of cyclotomic extensions. And if you remember where we're going in the playlist on Galois theory, we're trying to prove a theorem that we used in the video on solvability by radicals, which is that for characteristic zero fields, radical extensions are always contained inside finite solvable extensions, and finite solvable extensions are always contained inside radical extensions. In that video, we used this fact without proof to then get Galois' characterization of when a polynomial is solvable by radicals over a field with characteristic zero. So we're now coming back to try and prove that lemma on which our proof in that video sat. And to prove those things, an understanding of cyclotomic extensions is going to be important. So firstly, I'm going to define what a cyclotomic extension is, and then we are going to look at a proof that cyclotomic extensions are always abelian. That's going to be the main goal for this video. And to make things simpler, I am going to make a simplifying assumption, which will be fine for where we're going to need to apply our knowledge of cyclotomic extensions. So firstly, in full generality then, what do I mean by a cyclotomic extension? So let F be a field, then I can create what is called the nth cyclotomic extension, which I'm going to denote like this. So F and then superscript and then n in brackets like this. This is my notation for nth cyclotomic nth cyclotomic extension of F. And of course, this isn't my notation, this is a standard notation, but this is the one that I like to use. And n, of course, is some natural number. Now, what does this mean then? What is the definition of the nth cyclotomic extension of F? It means the splitting field over F of the polynomial x to the n minus 1, which is a valid polynomial in any field, because any field is always going to have the element 1, which is the coefficient of this term, and then minus 1, which is the coefficient here. So if you take the splitting field over your field of the polynomial x to the n minus 1, i.e. you join on a bunch of nth roots of unity, then that field that you then get is the nth cyclotomic extension of F. Now, it might be the case that the nth cyclotomic extension of F is just equal to F if the polynomial x to the n minus 1, if this polynomial here, if this splits already in the field F down into linear factors, then the nth cyclotomic extension of F would just be equal to F. But in many cases, it's not going to just be equal to it, and it's actually going to be a proper extension of F. So that's the definition of the nth cyclotomic extension of F. I suppose we should just do an example. So if we have the rational numbers, and we take the second cyclotomic extension of the rational numbers, then that's an example where it will just be equal to the rational numbers itself, because we're taking the splitting field of the polynomial x squared minus 1, which already splits into x minus 1 times x plus 1 over the rational numbers. So you're not, the splitting field over the rational numbers of x squared minus 1 is just equal to the rational numbers. Whereas if you instead take the third cyclotomic extension of the rational numbers, so Q3, then we would be taking the splitting field of this polynomial over the rational numbers, and that polynomial does not split over the rational numbers. It splits into x minus 1 times x squared plus x plus 1, but then this polynomial is irreducible over the rational numbers. So it doesn't split into linear factors, so you would then have to take the rational numbers and join on a root to that irreducible polynomial. So you take the ring of polynomials over the rational numbers, and you quotient out by the principal ideal generated by x squared plus x plus 1, and that will give you the third cyclotomic extension of the rational numbers. So there's some basic examples, and we could go on. You could look at the fourth cyclotomic extension of the rational numbers. In fact, I might just do that one. So the fourth cyclotomic extension of the rational numbers. And by the way, there's another maybe more intuitive way of thinking about the third cyclotomic extension of the rational numbers. So, the rational numbers sits inside a much bigger field, which is the complex numbers, which is algebraically closed. So certainly, the algebraic closure of the rational numbers is a subfield of the complex numbers. So we actually call the algebraic closure of the rational numbers Q bar. It's called the field of algebraic numbers. So the third cyclotomic extension of the rational numbers, in fact all algebraic extensions of the rational numbers, are going to sit inside its algebraic closure, which sits inside the complex numbers. We often prefer to think of it sitting inside the complex numbers because this thing is something we're more used to. We have more intuition, we have analytic intuition for the complex numbers, whereas this thing is something that we have less intuition for and is still a massive mystery in algebra and pure maths. Anyway, we can now think about what this is, the third cyclotomic extension of the rational numbers, as a subfield of the complex numbers. So you just need to put on all of the third roots of unity in the complex numbers, and that will give you the third cyclotomic extension of the rational numbers. So in fact, all you need to do is join on 1, which is the primitive third root of unity, which will denote zeta 3. And I'll let it mean the canonical one, so e to the 2 pi I divided by 3, which we could try and actually work out what that is. I think it's minus a half plus root 3 over 2i, if I'm correct. I think on the argand plane it would be here, and I think this would be a half, and this would be root 3 over 2 in the imaginary direction. Or this would be minus a half. Sorry, that's zeta 3. That's not equal to the field, obviously. So if you join on that element, then you immediately get the other one as well, because the other one is just zeta 3 squared. That's the other third root of unity that isn't just 1. And therefore this would be a splitting field for that polynomial. It would contain the 3 roots of unity in the complex plane. So that's another more concrete realization, if you like, of the third cyclotomic extension of the rational numbers. So now the fourth cyclotomic extension of the rational numbers. Here you need the polynomial x to the 4 minus 1 to split. This over the rational numbers breaks down into x squared plus 1 times x squared minus 1. X squared minus 1 we know splits into x plus 1 times x minus 1. So actually all we need to do is stick on the roots to x squared plus 1, and of course the roots to that are I, so this is just q adjoin I, a subfield of the complex numbers. And more generally, the nth cyclotomic extension of the rational numbers would just be q adjoin zeta n, where zeta n is the canonical primitive nth root of unity in the complex plane, so e to the 2 pi I divided by n. The moment you join on that, you get all of the nth roots of unity, and therefore this will be the splitting field of the polynomial x to the n minus 1 over the rational numbers. Right, so now more abstract again then, so the end of examples, and let's go back to abstract stuff, and we want to prove that cyclotomic extensions are always abelian. Now they are always abelian, but I'm going to simplify it just to make things easier. I'm going to assume that the characteristic of my base field does not divide n, so I'm going to assume that the whatever cyclotomic extension I want to take, so n is my n in nth cyclotomic extension, I'm going to assume that it is not divisible by the characteristic of the field, because things are simpler in this case. You can prove the same thing holds for the more general case, but we don't need it, so I'm not going to bother doing that. So we've got our field here of characteristic f. I mean, all we're going to need it is in the case of characteristic 0. So in the case of characteristic 0, you could let n be whatever you like, and this condition is going to be fulfilled. So it's going to be absolutely fine for what we need it for. We could have had the simplifying assumption that the characteristic of the field is just equal to 0, because that's all we're going to actually need. But I'm going to do this slightly more general case, because the proof is pretty much the same. It just changes slightly when you allow also to have the case where the characteristic of the field does divide n. so we won't bother with that case. So you've got f here of characteristic f of this characteristic here, and then we're taking the nth cyclotomic extension and we're assuming the characteristic of f does not divide n. Now, the key thing about the reason I've insisted that is because this polynomial is then going to be a separable polynomial over f as long as I have this condition, because the derivative of it, if we call this polynomial p of x, its derivative, its formal derivative, no analysis here, its formal derivative is going to be nx to the power of n minus 1. And the problem is that if the characteristic of the field divided n, then this would be equal to 0. But because the characteristic of the field doesn't divide n, then we know that this doesn't equal 0. This coefficient here doesn't equal 0, so we get a non-zero polynomial here as the derivative. Now, this polynomial can only have one root, therefore, and that root is x is equal to 0. It's clear that this is just a monomial, this polynomial here. So its only root is x is equal to 0, and that is clearly not a root of this polynomial. If you stick 0 in here, you do not get 0. So we can therefore conclude the derivative and the polynomial do not have any roots in common in the splitting field of the original polynomial, and therefore we can conclude that the polynomial does not have any multiple roots in the splitting field of the polynomial, which is this nth cyclotomic extension. Therefore, it's a separable polynomial. And why do I want to know it's a separable polynomial? Because then I can conclude nice and easily that this extension here is finite Galois, because I know it's a splitting field of a polynomial that I now know is separable. And one of the characterizations of a finite Galois extension is just that it's a splitting field of a separable polynomial. So that tells me that the nth cyclotomic extension of f here is indeed a finite Galois extension. So this is a finite Galois extension. So the next question is, what is the Galois group of this then? So what is gal of the nth cyclotomic extension of f over f? How are we going to do this? So this is beautiful. I absolutely love this argument. And we're not actually going to... Well, maybe we are. Maybe we are actually going to find this Galois. No, we're not, I don't think. All I want to know is that it's abelian. Now, you might wonder, why am I so interested in that? If you watched the previous video in this playlist on solvable extensions, you'll know that a way that I can show that an extension is solvable is by showing that it's finite Galois, or finite solvable rather, is to show that it's finite Galois and to show that it's built out of a tower of abelian extensions. This is why I care so much about abelian extensions. So knowing that cyclotomic extensions are abelian is going to help me to prove that an extension is solvable. Because if I prove that my extension is finite Galois, and then I prove that it's built out of a whole bunch of, say, cyclotomic extensions, or, for example, Kummer extensions, which I also know are abelian because they're cyclic, if I show that it's built out of tower of cyclotomic plus Kummer extensions, then it will be built out of tower of abelian extensions, and therefore I can conclude it's finite solvable. So that's why I care about proving that cyclotomic extensions are abelian. Or cyclotomic extensions of characteristic zero fields is what we're really covering in our proof here, that those are abelian. The more general fact that all cyclotomic extensions are abelian is something that is true, but we're not proving that in full generality, but we're proving an adequate thing for the proof that we're aiming for. Right, so how am I going to do this? So I'm going to define something else, which is I'm going to define mu n of a field. And I'm going to define this to be the set of all nth roots of unity in that field. So it's everything, all little x's in big F, such that if you put little x into this polynomial, x to the n minus 1, it gives you 0. So collect all elements in the field F that satisfy this polynomial, stick them into a set, and I'm going to call that mu n of F. So it's just the set of all nth roots of unity in F. And then I'm going to think about mu n in the nth cyclotomic extension of F. And I know, given my assumption, I know this polynomial is separable. X to the n minus 1 is separable. Therefore, I know there are n roots of this polynomial in in the nth cyclotomic extension of F, I know there are no more, because if there were more than n, then that contradicts basic field theory. You can't have more roots of a polynomial than its degree. In any field, if you've got a polynomial of degree n, that field cannot contain more than n roots of distinct roots of that polynomial. So that's a basic fact from field theory that I assume you're comfortable with, that in any field, the number of roots of a given polynomial with coefficients in that field is less than or equal to the degree of that polynomial. So this is going to have cardinality, so if I put the cardinality symbols around n, and moreover, it's actually going to be a group under multiplication. So if I consider this set, mu n Fn, under multiplication, this is a group. So what do I need to do to show that it's a group? I need to show that it's closed. That's a big one. I need to show that it has an identity, so that's kind of clear. That's an easy one. 1 is clearly a root of this polynomial, so 1's going to be in this set. 1 is an element here. 1 is an element in this one as well. So you have an identity. I don't need to bother with associativity. I inherit that from the multiplication of the field obeying associativity. And then I just need to prove that inverses are also in there. So let's start with closure. So if I have two elements in here, so let's say x1 and x2 are elements of mu n Fn, then I just need to show that x1 times x2 is also in there. And the reason for that is that if I raise that to the power of n and subtract 1, well, this is the same as x1 to the power of n times x2 to the power of n, because multiplication is commutative. Each one of these is 1 because they satisfy the polynomial. X1 to the n minus 1 is equal to 0, and x2 to the n minus 1 is equal to 0. That's what this implies. So yeah, it's clear then that this is equal to 0 because 1 times 1 is 1. So that proves closure. Now multiplicative inverses. So let's say we have x is an element of mu n Fn. How do I prove that 1 over x is also an element of mu n Fn? So I need to show that 1 over x to the power of n minus 1 is equal to 0. Well, I could firstly, I should argue why 1 over x even exists. So it's because x obviously doesn't equal 0, because 0 is not going to be an element of here, because 0 is not going to satisfy the required polynomial. So x is a non-zero element of f, therefore its multiplicative inverse exists. So here, what I can now do is pull out 1 over x to the power of n, and I will get 1 minus, and then x to the power of n. And then because x is an element of mu n Fn, this is therefore equal to 0, and therefore 0 times 1 over x to the power of n is also equal to 0. So that proves that 1 over x to the power of n minus 1 is equal to 0, so therefore 1 over x is an element of mu n Fn. Good. So that proves that this is a group under multiplication. And then we use a fact from field theory, which I think I do prove in my playlist on field theory, a video I made long ago. We're going to use a fact from field theory, which is that if you have a finite subgroup of the multiplicative group of a field, then it is a cyclic group. So I can therefore conclude that mu n Fn, I know its cardinality is n, so I know now that under multiplication it is isomorphic to the group Cn. Great. Why does this help me? Why have I done this? Because what I'm now going to do is I'm going to show that my Galois group of Fn over F is isomorphic to a subgroup of the automorphisms of this. And I know what the automorphisms of the cyclic group are. Group automorphisms here. So let me just argue why this is the case. So what I'm now going to do is I'm going to create a group homomorphism. But firstly, just think of it as a map, which is phi, which is going to map my Galois group, the elements of my Galois group, and I've already argued that this is a finite Galois extension, so it will have a Galois group, and it's going to map them onto group automorphisms, so aut meaning group automorphisms of mu n fn, like that. Excellent. And how is it going to do it? It's going to take any automorphism here, which is a field automorphism of fn, and it's going to just restrict it. It's going to map it onto its restriction to mu n fn. So, let me argue that this is a well-defined map then. So, firstly, think about what... well, obviously, we need to think about what this is going to do, this restriction. So we have our entire field here. So this is Fn, the nth cyclotomic extension of F. And then we have this tiny little subgroup. I'm going to draw it quite big, just for the sake of the picture, which is mu n Fn of the nth roots of unity in Fn. And we have this map mu, which is a map from Fn to Fn, and we're now restricting it to just being on this set. What does that do? What is this map then restricted? So the first thing really I want to convince you is that this map, sigma restricted to mu n Fn, that this is a map from mu n Fn to mu n Fn. So I need to, I want to actually convince you that it becomes a group automorphism of mu n Fn. But for that to hold, I definitely need it to be the case that it actually is a self-mapping of mu n Fn. If it's not a self-mapping of mu n Fn, then it's absolutely got zilch chance of being a group automorphism of it. So I need to prove that my field automorphism mu does indeed send everything in mu n Fn onto something in mu n Fn. I also need to prove that this map is a bijection, because automorphisms, I want it to be a group automorphism, and group automorphisms are bijective self-mappings. But firstly, let's just start with self-mapping. So it's because it's a field automorphism, so it has to map things that are roots of the polynomial xn minus 1. Well, it's more than that. It's because it's a field automorphism that fixes the base field F. So being in the Galois group, it means you're a field automorphism of the top field that fixes the bottom field. This is a polynomial over the bottom field, so it fixes this polynomial, sigma. And therefore it has to map roots of this polynomial to roots of this polynomial. Therefore, that's why it has to map everything in here onto something else in here, because this is all the roots of this polynomial. So that's the first part. Why is it going to be a bijective self-mapping? So injective, it inherits injectivity from the larger thing. So sigma was a field automorphism of Fn. Ergo, it had to be a bijective self-mapping of Fn. Therefore, the map was injective. Therefore, when you restrict it down, it's still going to be injective. So that gives us injectivity. So I can draw the little curve there. Surjectivity, it's because, it's a finite map now. It's a map between finite sets. This is a finite set. So just by the pigeonhole principle, it's mapping everything here. This is a set of size n onto a set of size n, and it's doing it injectively. Therefore, it has to be surjective. That's the only way it can happen, because they're finite sets. So we get, therefore, that it's a bijective self-mapping, this restriction of sigma to mu n Fn. Now I need to argue, why is it actually a group automorphism? Why is it going to be in the set of group of group automorphisms of mu n Fn? Well, it's because it inherits that from the field automorphism again. What is the requirement to be a group automorphism here? Or let me just think for a second. Let's think about what the requirement to be a group automorphism here is. It means that, it's exactly that, it just inherits it from the larger group. So this is just the set of all nth roots of unity in this field under multiplication. Therefore, to be an automorphism, you have to be a self-mapping such that sigma of, let's say, x1 times x2, which is the operation in the group, it has to equal sigma of x1 times sigma of x2. But it's going to inherit that from the fact that it was just a field automorphism restricted down. So because it was a field automorphism, it had to obey this for multiplication. So it just inherits that from the fact that it was a field automorphism. So yes, it is obvious then that when you restrict the elements of the Galois group like this down to mu n fn, that they are going to become automorphisms of mu n fn. Sorry, I just paused the video because there was a racket happening outside, which is sort of ongoing, but at least it's slightly better now. So let's continue. So I had hopefully convinced you that I can create this mapping phi from the Galois group onto the group of automorphisms of mu n fn just by restricting the field automorphisms of fn which fix f to the set mu n fn. Now what I want to convince you is that this map phi is actually an isomorphism of groups, and I also want to convince you that it's actually an injective, not an isomorphism of groups, it's a homomorphism of groups. I want to convince you that it's a group homomorphism, and then I want to convince you that it's an injective group homomorphism, and therefore that the Galois group of Fn over F is therefore isomorphic to the image under this map. And then I'm going to argue that this group of automorphisms here is an abelian group, and therefore I'll be able to conclude that the Galois group being isomorphic to a subgroup of that therefore has to be abelian also. And then I've done what I set out to prove, which is that for this case where the characteristic of f does not divide n, then you can conclude by the proof that I've given here that the Galois group of Fn over f is an abelian group, and therefore that this extension is a abelian extension. So let's do group homomorphism first. So why is this a group homomorphism? So if I have two field automorphisms here, sigma 1 and sigma 2, and they're being composed together, why does it not matter whether I firstly compose them together and then do phi of them, or if I firstly do phi of them and then compose them together afterwards in this group? Why is that the case? So what is phi of sigma 1 composed with sigma 2? Well, this means do sigma 1 second, so do sigma 2 first. So we'll use the normal convention, which is that this one is done first. So you do this automorphism first, then you do this one, and then you are going to restrict the whole thing down to just being on mu n fn. Okay? Whereas on this side, what does this mean? This means that firstly what you do is you restrict down. So you do sigma 1 restricted down firstly. I won't keep writing the full thing out, I'll just write mu n. And then you restrict sigma 2 down, and then you compose them together. Why does it not make any difference? Because it doesn't matter whether you firstly restrict down, which is what you're doing here, and then compose them together, or whether you firstly compose them together and then restrict down. The composition is actually exactly the same. It's just about what you're looking at. So, you know, when you compose sigma 1 with sigma 2 like this, yes, you've restricted them down to here, but the composition is still exactly the same as what you were doing if you were looking at the entire thing, Fn. You're still composing them together as maps. It's just now that you've discounted all of this bit around here, but that doesn't matter. So hopefully this is kind of obvious that this is going to be a group homomorphism. Because it truly, you know, here we're just composing these two maps together and then just saying all I care about is what actually they were doing on here. Here we said get rid of this bit first and then just compose them together, but what you overall end up with as a map acting on here is going to be exactly the same. It doesn't matter which way round you went to achieve it. So it is reasonably trivial that this is a group homomorphism. Why is it an injective group homomorphism? That's a bit more interesting. So let's imagine it wasn't. Let's imagine we had, in fact, let's imagine we need to look a little bit more actually back over here at this nth cyclotomic extension of F. So I argued that mu n Fn, the subgroup of Fn consisting of all of the nth roots of unity, I argued that it was isomorphic to a cyclic group. We used that theorem from field theory to conclude it was isomorphic to a cyclic group. That means there is a generator of that cyclic group. We will call that generator zeta n because it's going to be a primitive nth root of unity. Generators of this group of nth roots of unity, those are called primitive nth roots of unity. So select one of them. You might like to select, there are multiple different generators in general of a cyclic group. So you could select any of the generators of that cyclic group, and all of them could wear the crown of primitive nth root of unity. In the complex plane, we obviously have a canonical one, which is the e to the 2 pi I over n. But in more general fields, it might not be obvious at all which one is the canonical one, so you could pick any of them. But pick one of them and call it zeta n. Then if you consider f adjoins zeta n, this is equal to the nth cyclotomic extension of f, because once you've got zeta n in, you will have the whole of mu n Fn in, because you've got all powers of zeta n. You've got zeta n squared, zeta n cubed, etc. And those powers, they generate the entire group of nth roots of unity. They generate the entirety of mu n Fn. And then once you've got the entirety of mu n Fn in there, you are, by definition, the nth cyclotomic extension of f. So the nth cyclotomic extension of f is a simple extension generated by a primitive nth root of unity. Now, that means that when we're considering field automorphisms of Fn, all I need to know is where the generator goes. I just need to know where zeta n goes. So that means that each one of these is characterized by where it sends zeta n. So if I had two elements of the Galois group that were being mapped onto the same thing in this group of automorphisms, the problem with that is that the automorphism over here is also determined by where it sends zeta n. So let's think about the elements over here. In fact, this is a good thing to do. So we have our group mu n Fn. This is equal to the group generated by zeta n. So it's equal to 1, the set 1, zeta n squared, all the way up to zeta n to the n minus 1. That's it as a set. The whole thing's generated by zeta n. So if you're going to be a group automorphism of this cyclic group, what you are is completely also determined by where you send that generator, where you send zeta n. So if I have got some, let's say, I need a different letter to call it. Let's call it tau. So I've got a tau in this automorphism group of this cyclic group here. It is completely determined by where it sends zeta n. If you tell me where it sends the generator of the cyclic group, so it'll have to send it to some other power of zeta n, then that completely determines where everything else goes, because once I know where zeta n goes, zeta n squared has to go to, zeta n squared is zeta n times zeta n, and therefore tau of this has to equal tau of zeta n times tau of zeta n, and therefore by knowing what tau of zeta n is, it completely determines it. So for all powers of zeta n, they're determined by where you sent that original zeta n. So this is why you can't have two field automorphisms going to the same one here when they're restricted down to this set, because then they'd be sending, if they're the same over here, they'd be sending zeta n to the same thing, but if they send zeta n to the same thing, then they are the same field automorphism. So no two distinct elements of the Galois group can be sending zeta n to the same thing, and therefore they can't be equal to the same automorphism over here when you restrict down to mu n Fn. So that's why it has to be injective. So what we've overall got here is this map phi from the Galois group of Fn over F to the automorphism group of mu n Fn. This is an injective group homomorphism, and it's achieved just by restricting the field automorphism down to mu n Fn. Therefore, this is isomorphic to the image, so this group is isomorphic to the image of phi, which is some subgroup of the automorphism group of mu n Fn. Now, what is the automorphism group of mu n Fn? So, mu n Fn, I know that this is isomorphic to the cyclic group of n elements. What is the automorphism group of the cyclic group of n elements? It is equal to Zn cross, the group of units of the ring of integers modulo n. Maybe I should just give an argument as to why that is. Hopefully you already know this as a fact, that the automorphism group of the cyclic group of n elements is isomorphic to Zn cross. But just in case you don't, let me give an argument as to why it is. So Cn is isomorphic to Zn under addition. So in the language of addition, 1 is a generator of this cyclic group, and therefore any automorphism that you have of this group, so when just in the new notation, we're looking at the automorphisms of Zn under addition, this group, any automorphism in there is completely and utterly determined by where it sends 1 to. So once you know where 1 goes, everything else is determined, because for anything else you just split it into however many 1s you need added together to get to that element, and then you just map it onto whatever 1 went onto that number of times. So for example, 3 is equal to 1 plus 1 plus 1, so whatever your automorphism sigma sent 1 onto, you'd then map 3 onto sigma of 1 plus sigma of 1 plus sigma of 1. 1, because it's a automorphism, it's an isomorphism, therefore 1 is going to have to be mapped onto another generator of this group. You can't map 1 onto something that isn't a generator of this group, because then it's not going to be bijective in that case. It's not going to be surjective, because if something's not a generator, the only elements that you're going to get in your image of your map are going to be things that you can get to by adding whatever 1 is mapped onto however many times together. So, if you're mapping it onto something that doesn't generate the entire group, then the image isn't going to be the entire group, because the image is going to be what's generated. The image is going to be the subgroup generated by sigma of 1. Therefore, sigma has to map, any automorphism has to map 1 onto another generator of Zn under addition. Now, what are the generators of Zn under addition? Well, they are the elements of Zn cross. They are the elements that are co-prime to n. The things that have multiplicative inverses in the ring of integers under modulo n. Fine. So the only things that I can possibly map 1 onto then are the things in Zn cross. And so my contenders then for automorphisms are all the things that map 1 onto I, where I is an element of Zn cross. So now I just need to convince you that all of these options, you let I equal any of these, that they all successfully are actually group automorphisms of Zn under addition. And let's think about, if we call sigma I, in fact I'll put it here, if we let sigma I equal the map that sends 1 onto I, and then it sends everything else, all other, let's say, x, onto I plus itself, however many times. So this is x number of times. So if x is 2, you'd add I to itself 2 times. If x is 3, you'd add I to itself 3 times. This is just saying exactly what I said up here, that you just add wherever 1 goes onto itself however many times you're looking at to get where your element goes. So we can write that more simply. It's I times x, and obviously it's modulo n. You do that multiplication modulo n, so I'll put that here. It's that multiplication modulo n. Right, so these are my contender maps then. Sigma I maps x in Zn under addition, and it maps it onto Ix. Why is that a group automorphism? Well, I just need to check that. I've already argued that it's going to. It's forced to be bijective because it's going to be surjective. If you map one onto another generator of this group, then the image is going to be the entire thing back again. And then because it's a finite set and it's a surjection, then it's surjective self-mapping, then it's forced to be injective. So they are bijective. So these mappings are bijective self-mappings. I just need to argue why they're also group automorphisms. So for that, I just need to check that if I put in x1 plus x2, that this is equal to sigma I of x1 plus sigma I of x2. Well, the reason for that is that this is equal to I x1 plus x2, which is equal to I x1 plus I x2, which is of course equal to sigma I x1 plus sigma I x2. So that's the group automorphism condition, or the group homomorphism condition checked. So that proves that all of these maps, these sigma I maps, they are indeed automorphisms of Zn under addition, and I've also argued that they can be the only things that were possible contenders for being automorphisms. Therefore, these are all automorphisms. Now I just need to think about, okay, that's a list of all of them, but how does composing them work? Because I want to know what is the structure of my group of automorphisms. So I know what it is as a set. It can be characterized as Zn cross. I want to argue how, if I put multiplication here, that this is actually isomorphic as a group. So why is it the case that composing these maps together is the same as multiplication modulo n? Well, that kind of is obvious. So, if I do sigma I composed with sigma j, what is this map here? Well, it's going to map. If I think about what it does to each x, well, I'm firstly doing sigma j, so that will multiply x by j, and then I'm doing sigma I, that will take whatever's left and multiply it by I, and all of this multiplication is being done mod n, but of course multiplication mod n obeys associativity, so this is just ij times x, like so, so yes, it is obeying that, so this is the same then as sigma ij of x, where you've multiplied I and j together mod n to get something that's back, between 0 and n. So that is therefore the argument as to why you want all of these elements, and then the composition of the maps is isomorphic to multiplying these elements together. And we know from basic ring theory that this does form a group, the group of units of the ring of integers modulo n. Now, this is an abelian group also because it's a subgroup of the multiplicative group of Zn. It's a subgroup of the multiplicative group of Zn, and this is a commutative ring, therefore this is an abelian group. And that's what we wanted to know overall. So we've now argued that the Galois group of our nth cyclotomic extension of f over f is isomorphic to a subgroup of Zn cross, which is an abelian group, and therefore is abelian itself. And that's all I want you to take from this. I don't care what the actual group is itself, I just need to know that it's abelian. So I think we'll end there. Thank you for watching. Sorry,